Hey, fourth grade students, I hope you all are having a great day. I'm not for sure if you're watching this on a Monday or Friday, but whatever day it is, I hope it is fabulous. So, this week we have been learning all about waves. I know you've been with Miss Meeks. I know you, not Miss Minks, that's her maiden name, Miss Aubrick, and then as well as Miss Pergram. And we are going to continue on with that today. So, we are going to do the third mystery science, and this may be broken up in between 2 or 3 days. We'll see how much we can get done. So we are going to listen to Doug explain some waves.
Hi, it's Doug. There are probably lots of sounds that you like to hear. Imagine the sound of waves crashing at the beach, or the sound of people laughing and having a good time. Or you probably have a favorite song or a musical performer. Those are sounds you like. But are there sounds you dislike? I'll tell you about one that will probably drive you mad. It's a sound made by an invention called the mosquito. That's this speaker here. You see, one day back in 2005, the owner of a convenience store was having problems with some teenagers hanging around outside his store. They were causing trouble, speaking rudely to the customers as they walked in, that kind of thing. An inventor heard about this problem and came up with a solution. The inventor knew about a certain sound, a sound so high that actually not everyone can hear it. And that's what's so remarkable about this sound. It's a sound that can only be heard by people under the age of 25. The reason is that once you're older than 25, your hearing starts to get a little worse, and so you just can't hear really high sounds. This really high sound sounds like a really high-pitched whistle, or the annoying buzz of a mosquito in your ear. If you're under the age of 25, it's definitely not a sound you'd enjoy hearing. So the inventor's idea was to blare this sound from a speaker outside the convenience store, which stopped teenagers and anyone under the age of 25 from wanting to hang around out there. And it worked. Not everyone agrees it's a great solution, though. Some people have pointed out that there's plenty of teenagers it bothers who aren't doing anything wrong. Not to mention, it also would bother any little kids coming near the store. But some teenagers have turned this whole idea on its head, and they've gotten their revenge. There are ringtones for cell phones which use this sound, and so some teenagers have used this secret high sound in order to send text messages to each other in class without their teacher noticing. And it works. The sound is really high. It's so high that a teacher can't hear it. You know that sound is a vibration. So if all sounds are just vibrations, what is it that makes some sounds different from each other? Like, what is it that makes the mosquito sound super high and other sounds so much lower? Are the vibrations of high sounds different from the vibrations of low sounds in some way? What do you think?
All right, guys, pause the video right here, and write down your answers in your science journal. We know that sound is a vibration, but what makes one sound lower and another sound higher? Think about that. Write it in your science journal. There is not a right or wrong answer. These are just questions to let your brain think. Pause here and write your thoughts down. All right, we are going to go on.
Why are some sounds higher and others lower? Is there something different about their vibrations? It would help if we have a sound maker that lets us see the vibrations being made. Then we could get a closer look at them. What we need are some musical instruments that we can experiment with. Like, I have a guitar. Now, first of all, notice that when we talk about how high or how low a sound is, we're talking about something different from just how hard or strongly you hit them. Watch. Strumming a guitar gently or strumming it hard doesn't change how high or low the sound is. It just changes how quiet or how loud the sound is. We call that the sound's volume. When we're talking about how high or how low a sound is, that's what we call the sound's pitch. Let me show you what I mean by that. Here's a note with a high pitch. And now here's a note with a low pitch. A guitar is an instrument that can make both really high-pitched sounds and really low-pitched sounds. But there are some instruments that are more limited in their range, like a flute. really only capable of making high-pitched sounds. What about an instrument that only makes low-pitched sounds? I can think of no better example than a tuba. So what makes sounds have a high pitch or a low pitch? Well, we know sound starts with a vibration. So let's look at the vibrations that make these sounds. These are a guitar's strings seen close up. Let's compare the vibration of a guitar string when we make it high pitch and low pitch. Now here, I'm going to pluck the string and get a high pitch. Now, let's hear a low pitch. I'm going to pluck the same string, but I've got it tuned very low. Did you see any difference in how they vibrate? It's hard to tell unless we compare them side by side in slow motion, like this. See any difference now? How do the vibrations look for sounds with a high pitch versus sounds with a low pitch?
All right, pause the video. What differences do you see between a vibration that creates a high pitch and a vibration that creates a low pitch? Pause the video right now. Write that, jot your thoughts down in your science journal. All right, friends. So, of course, you all do not have a copy of our science worksheet, but we will fill this out together, okay? And you might want to pay attention because this could be a part of your Google exit slip, okay? So let's read, or let's watch, Doug.
So now you've seen that the vibrations I create when making a high-pitched sound and a low-pitched sound look different from each other. I noticed that when I made a high-pitched sound, the vibration moved back and forth more quickly. It looked fast. When I made a low-pitched sound, that vibration looked like it wobbled back and forth a bit more slowly. So what about the vibration as it comes to my ear? When you're listening to a guitar, for example, you know that those vibrations from the guitar strings have to travel through the air to get to your ears. It would be nice if you could see those sound vibrations as they travel through the air, not just the vibrating string that made them. Well, it turns out there is a way to do that. Scientists have actually invented a way to see sound vibrations as they travel through the air. They use this special setup. It's a slow motion camera plus some very special lighting conditions, and that allows them to see what's happening in the air when a sound is made. Here we go. This is the sound of a book landing on a table. Watch that again. You can see the vibrations move outward. And here's a speaker playing music. And finally, the sound as a firecracker explodes. Let's see that again. Whoa. Does this remind you of anything? To me, it looks like a ripple in a pond. Like if you drop something in water, right? And the ripples spread outward. It might surprise you that sound vibrations in air look like waves or ripples. But think about those ripples you see on the surface of water. Where do they come from? The ripples come from something vibrating the water. When I vibrate my hand on the surface of water, it creates a ripple or wave that spreads outward from the vibration, like this. And just like in water, when a sound maker vibrates the air, the vibrations travel outward as ripples or waves of air. So sound vibrations are traveling waves in the air. Sound is a wave. You've just seen visual proof of it. So knowing that sound is a wave, we can ask, do high-pitched sounds and low-pitched sounds make different waves? You could find out for yourself if only you could set up this slow-motion camera technique in your own classroom. That way you could experiment with making different pitches, and so just seeing what kind of sound waves they make. Unfortunately, this camera setup is not easy. But there's another way for us to see sound waves. Instead of having a direct camera view of the air, we can use a machine that will do something similar. It's called an oscilloscope. It takes sound from the microphone, like on your computer, and shows the sound vibration waves, not from top down, like ripples in a pond, but in more of a sideways view, more like a classic wave, like this, the kind of waves you draw if someone asked you to draw ocean waves. So I'll try talking into an oscilloscope right now so that you can see what it looks like. See, here I'm talking right now, and you can see a line moving on the screen. This line is a sort of picture of the sound waves. It's not showing me the real sound waves themselves. It's more like a graph, kind of like a diagram. But the diagram changes in response to the real sounds I'm making right now. There's a lot going on here. And a lot of it doesn't really look like nice smooth ripples or waves. It looks like the ocean in a storm. So I played around with lots of sounds, and I found out that a whistle like this made a nice wave. Now watch as I make a low-pitched sound. And now a high-pitched sound. It's hard to see what's going on. Everything moves so quickly. So I'm going to use a button that freezes the picture. Here's the high-pitched sound again. Just listen. Okay, draw that on your worksheet. Be sure you draw just as many waves as you see on the screen. You can pause the video if you want so that you have more time to draw. Okay, I'm going to move on.
All right, friends. So for our exit slip, we may not be able to draw what we see, but we will be able to fill out the other information.
To the low-pitched sound now. Here's a low-pitched sound again. And I froze it so you can get a good look at it. Now draw what you see on your worksheet. Be sure you draw just as many waves as you see on the screen. Again, you can pause the video if you want to, so you have more time to draw. So can you see a difference in how the sound waves look as viewed here from the side? How would you describe the differences between a high-pitched sound wave and a low-pitched sound wave?
All right. This is where we are going to end the video at today. You are going to use these two pictures to finish your exit slip, okay? You already know that the high pitch wave goes really, really fast. And we then know that our low pitch goes very slow. So then on your exit slip, you are going to tell me, is the high pitch, are these more squished together or farther apart? And then you're going to do the same thing on the low. We will continue our video tomorrow. I hope you all have a wonderful, wonderful day, my friends. Bye, guys.